Okay, let's start. On the left here, you see a still picture that represents the burst of radiation emitted by two black holes going around each other and merging. The very first detection that happened the 14th of September 2015. So I will start by reviewing briefly what are gravitational waves, which kind of unique information they bring to us, how do we decode the gravitational signals, how we interpret them and extract information about the sources. I will give you some highlights on astrophysics, cosmology, and fundamental physics that we could extract from the signals with the LIGO and Virgo-Kaga collaboration. And then I will describe which kind of advances in theory and also that analysis will be needed with the next generation detectors on the ground and in space, and also the upcoming runs in this decade. So let me start. So the waves were predicted by Albert Einstein in two papers in 1916, 1918. So here you see the Einstein equations in full glory. So the curvature geometry of space-time on the left and mass energy on the right. And Einstein linearized this equation with respect to a Minkowski flat space-time, and in a particular gauge, he could write the propagation equation in this form, where the box here is the D'Alembert operator. So for people here, well, actually, everybody here who has taken a course in electromagnetism can recognize this equation in the case of electromagnetism, but here we have the energy momentum tensor on the right-hand side and the tensor on the left-hand side. So the waves are produced by coherent acceleration of mass in the form of matter or just warp space-time. This will be the black holes. And the waves are produced, as I said, by the accelerated motion of mass and energy that deform the space-time around the sources and propagate at the speed of light away from them. And what is also important is the way in which a gravitational wave interact. We will see it's a key way, the key idea underpinning the gravitational wave interferometers, the impact of gravitational waves on free-falling bodies. Like, for example, in the ring, this tube, the rings are affected by the passing of the gravitational wave that you see in this animation. Sometimes we show this plot here, this video here. It's an exaggerated, very exaggerated impact of the gravitational wave on the Earth. In fact, the waves are very weak, and in order to produce waves that we can detect on the Earth, they have to be emitted by so-called compact objects, black holes or neutron stars that accelerate and move almost at the speed of light. And these are black holes and neutron stars. So a few words about black holes. So black holes are just warp space and time. There is no matter. The astrophysical black holes come from the collapse of stars with a mass larger than 20, 30 solar masses. We can also produce, we think black hole can be also produced by overdense regions in the early universe, and in this case they are called primordial black holes. And as maybe you know, nothing can escape the so-called horizon of a black hole, matter or light. And just to give you an idea, if you take a black hole which has a mass 10 times the mass of the sun, the so-called radius of the black hole is just 30 kilometers. And you can contrast that with the radius of the sun, which is 700,000 kilometers. So you have a lot of energy in a very small region of space-time, and that's why these objects are compact. And they have a very big exert a very big gravitational pull in the environment around them, including light, as you can see in this picture here, how the light from stars or galaxy around the black hole can be distorted. Despite being very mysterious, the black holes are very simple objects. They are only described, the astrophysical one, by two numbers, the mass that determine basically the radius, and the spin that determine the shape of the object. A few words about neutron stars. They also come from the collapse of stars, but smaller stars than the one that produce black holes. And neutron stars are also quite compact, slightly less compact than black holes. Their masses are between 1 and 2 solar masses, And the radius ranges, well, we don't know yet, but we think is between 9 and 13, more or less, kilometers. One of the open questions for neutron stars is what they are made of, especially in the core. And we will see how gravitational waves can answer these kind of questions. Now, black holes in the universe actually come with different masses. So in this plot here, in the region here on the left, these are the masses that LIGO-Virgo-Kaga collaboration are actually observing between a few solar masses up to 100 solar masses. But we see actually black holes in the universe up to tens of 100 billion solar masses. The black hole at the center of our galaxy, Sagittario A star, has 4 million times the mass of the sun. One important point is that even if black holes are very simple objects, they actually play a very important role in the universe. They have a symbiotic relationship with the galaxy. They influence the growth of structures on large scale. And black holes of smaller size, 150 times the mass of the sun, are also important in determining the evolution and even the survival of clusters of dense stars, as you can see in this plot here on the right. So one of the important questions in astrophysics is how actually the black holes with very large mass form in the universe, especially starting from, considering the fact that we have observed also black holes of much lower masses. And in fact, one of the questions that we want to address with gravitational waves is actually to understand the growth of these large black holes. We think that black holes grow their mass through accretion of gas and also through merger, as represented in this merger tree here in the bottom right part of the slide. Because normally these big black holes are at center of galaxies. Okay, so just one slide to summarize at least the main way in which we observe black holes and neutron stars. So the very first stellar origin black hole that was observed was in the 70s. Cygnus X1 is an X-ray source. The black hole is in a binary with a supergiant star. And the material falls into the black hole, is heated up, and emits X-ray. And that's why the way in which we have detected this system, and also because of the periodic motion of the giant star, we can, through the Kepler law, actually determine the mass of the black hole. Actually, this method is also used to determine, through the motion of the stars around Sagittario A star, that at the center of our Milky Way, there is actually a black hole of 4 million times the mass of the sun, as I was saying before. Today we have pictures of black holes, as this one, through the Event Horizon Telescope collaboration. This is Sagittario A star, and pictures have been taken also of the black hole at the center of Messier 87, a close galaxy to us. And of course, with gravitational waves, we can actually observe for the first time a binary with two black holes going around each other and then merging with each other. And because this event cannot emit any light, in the case of stellar origin black holes, the only way that we could observe this system was through gravitational waves. Now, a few words about the neutron stars. So we observe neutron star mainly through pulsars. So a pulsar is highly magnetized neutron star which emits a beam of radiation in the radio, as you can see from this animation there. And amazingly, we have seen neutron star pulsars in a binary system, like this double pulsar that was discovered in 2003. And we detect on the Earth these pulses coming from the pulsar, and by measuring the variation in the pulses that arrive on the Earth due to the fact that the pulsar is actually in a binary, we could even, determine that the system was emitting gravitational waves. That was the first actually strong, or actually I would say definite proof that gravitational waves existed. And finally, as I will also discuss later, this is a simulation of two neutron stars going around each other that refer to the event that was discovered by LIGO and Virgo the 17th of August of 2017. You see the two neutron stars going around each other, losing material now, and then, at least in this particular simulation, merging into a black hole. Okay, so gravitational wave astronomy, just to contrast with electromagnetic astronomy, spans many decades in frequency, as you can see in this plot here. So with LIGO and Virgo and Cagra are opening a very small bandwidth here between a few tens of hertz and a kilohertz. And sometimes, because this is in the audible, the 100 hertz, so we call them also sounds. Last June of last year, the pulsar timing array collaborations have also announced a possible discovery of a gravitational wave background, possibly coming from supermassive black holes. This is in the nanohertz. And we expect in the near future that we might observe the polarization in the cosmic microwave background radiation that would be imprinted by gravitational waves present at the last scattering surface. Now, from the point of view of binary systems emitting gravitational waves, the reason why we are actually sensitive to all these frequencies is because the gravitational wave is a multiple of the orbital frequency in the binary. And we can observe these binaries of different separation, when the black holes are different separation from each other, and this means basically different frequencies. And this means also that the black holes are in a different epoch of their life. They are maybe interacting with different kind of environment around them. Although I will not discuss this in my talk today, there are also other ways in which gravitational waves can be produced besides binary system. The collapse of stars that form black hole and neutron star can emit gravitational waves. The pulsars, the rotation of the pulsar can also emit gravitational waves. And the accelerated expansion of the universe, for example, in the epoch of cosmic inflation, could also produce gravitational waves. So today we have a new tool to explore the universe. So in the past, until more than 10 years ago, when we were seeing this kind of plot, we were mainly trying to actually probe the evolution of the universe through electromagnetic radiation. But now with gravitational waves, as you will see later, today we are exploring mainly up to a redshift of 1 or 2. In the future, we will go to 10, 20, even 100. And possibly in the next, certainly in this century, we might actually really go back to the very early universe to have a snapshot through the emission of gravitational waves. Okay, so now let's go to the binary systems. And I want to say a few words about the strengths of the gravitational waves. And I'm going to use just Newtonian gravity for this exercise and classical mechanics that I'm sure that all of you have taken a course on that. So if you have a binary system with two masses, M1 and M2, you can introduce the reduced mass and the symmetric mass ratio, the reduced mass divided by the total mass. And what Einstein proved in his papers is that the first multiple, I have a problem. 1 second, I have to go out and re-enter, I think. Yes. The first multiple that produces gravitational wave is actually the quadrupole, not the dipole, as in electromagnetic radiation. And the strain, so now I remove the indices, otherwise it would be a tensor here, is proportional to the second derivative of the quadrupole, is inversely proportional to the distance to the source, like in electromagnetic radiation, and it depends on the Newton constant and the speed of light in this way. Now, if you take a binary system, you can actually compute the quadrupole and also the second derivative of the quadrupole, and you arrive to a formula like this. This is the velocity in the binary, and c is the speed of light, and m is the total mass of the binary, and u is the symmetric mass ratio that I introduced here. So, for the moment, let's consider quasi-circular orbit, two objects that are going around each other on a quasi-circular orbit. In that case, just using the Kepler basically law, you can relate the velocity to the orbital frequency. Okay, so you realize here now that the farther is the source, the weaker is the signal. So in principle, we would like to have all our sources close by, okay? Like, for example, in our Milky Way. But actually, it's very rare to see two black holes or two neutron stars just in the last phase of their life before merging with each other. It will take a long time, more than a million years, to see an event like this in our galaxy. So we have to build interferometers, experiments that are sensitive to a very large volume that contains many galaxies, or cluster of galaxies, so that we can, likely have an event every year, or as it happens today, one event every 3 days, okay? So now, just to give you an idea, if you take a binary neutron star in the Virgo cluster, which is the closer cluster to us, 20 megaparsec, the strain H is very small, it's just 10 to the minus 21. It's dimensional, the strain. The luminosity, it's, however, very large. So the luminosity you can get by taking one-time derivatives of H, like in electromagnetism. You take one derivative of the electromagnetic field, the square, and you get this formula, and notice the dependence on the velocity divided by the speed of light to the power 10. This tells you that the object has to go at a speed very close to the speed of light, otherwise the luminosity will be very small, okay? It will decay very quickly with the velocity. Now, the typical gravitational wave luminosity is of the order of a fraction of 10 to the 52 watts, okay, 10 to the 59 erg per second, many orders of magnitude more than the luminosity of our sun in electromagnetic radiation. But this is mainly emitted at the very end, when the two objects are close to merging with each other. Furthermore, the waves are very pristine. They bring us real information about the source because they are not much affected by whatever they encounter as they are emitted up to they arrive on the Earth. Although, especially in the next runs and the new facilities, we have to care about phenomena like even gravitational lensing that the waves will be subjected to if they pass through a lens that could be a galaxy, quasar, etc. Okay, so I have this small animation to show you a few examples of, just 1 second, sorry. Okay, I don't know why some of the animation is not working. Let me go out again and then re-enter, sorry. Okay, so what you see here are the black some of the black holes that were observed by LIGO and Virgo, and at the bottom of this animation, you have the binary neutron star, and you can see the binary neutron star, the signal is much longer. In fact, it lasted for 3,000 cycles, starting from 30 Hertz up to the kilohertz. And the reason of the difference in the length depends again on the way in which the gravitational wave frequency depends on the mass of the binary, but also on the frequency at which the two objects merge with each other. So, as a rule of thumb, the frequency at merger is something like 4,400 Hertz divided by the total mass of the binary, unit of the mass of the sun. So if you take a neutron star, because the mass of the neutron star is 1 or 2 solar masses, it will merge in the kilohertz. And that's why the signal is very long, as you can see here. But black holes are more massive than neutron stars. We are seeing black holes of a few tens, 100 solar masses. So they actually merge more at lower frequency, and that's why the signal are much smaller. And that's why if you take a million solar mass black hole in a binary system, you have to go in space to detect these systems because they are going to coalesce at frequency much smaller than a few hertz. Now, the information on the properties of the black hole and neutron star are imprinted in the waveforms. We do Bayesian analysis, as you will see later, but just to give you an idea, the frequency is actually increasing over time because the system is emitting energy, so the binary shrinks until they merge. So the frequency is increasing, and from the frequency evolution, we can infer the masses of the binary. From the amplitude and the masses, we infer the distance, where the source was with respect to the Earth. From the fact that we have more than one detector on the Earth, we can obtain, from the time of arrival, the amplitude and the phase at the detectors. We can infer the sky location. And if we see modulations in the signal of this kind, which are different from what you see here, we can know whether the body were moving on an eccentric orbit or circular, whether the spins of the black hole were precessing or were non-spinning, or they were aligned with the orbital angular momentum, which is perpendicular to the orbital plane. And finally, if we compare the waveform with the deviation from general relativity, we can probe the theory of gravity. Is it general relativity or something else? So for that, gravitational wave interferometers have been built. So the LIGOs are in the US, we have CAGRA in Japan, not very far from here, the Virgo detector in Pisa. So these are interferometers that use this key idea I was telling you at the beginning, the way in which a gravitational wave interacts with free falling bodies, as you see in this animation here. So the free falling bodies are the mirrors that hang by wire at the extremity of the Fabry-Perot cavity of the interferometers. Notice the distance between the mirrors is 4 kilometers for LIGO and 3 kilometers for CAGRA and Virgo. And what this interferometer monitor or measure is the displacement of the mirrors at the level of 10 to the minus 16 centimeter if we want to measure H of the order of 10 to the minus 21, which was the strain I had in the previous plot, in the previous slide, about the neutron star in the Virgo cluster. Okay, but for what interests us, the binary systems, what is also important to realize is the way in which we detect the signals. We extract the signal from the noise. So we use match filtering or signal processing. And for that, we need actually to know in advance the templates, what are the shapes of these waveforms. And I have an animation here to show you how it goes. So we take the data that come out from an interferometer, and we have a template bank, a bank of templates, and we correlate the data with the template, which is in pink, and the upper panel is the correlation maximized on the parameter of the binary, and when we see a spike like the one you saw there, if the signal-to-noise ratio maximized goes above a certain threshold, which has been fixed depending on the knowledge of the noise, the false alarm probability associated to the noise of the interferometer, we can claim then a detection. And after that, we can do inference analysis, Bayesian analysis, to go after the event and extract the information. So for that, we need to know, especially because we use match filtering, very well, not just the amplitude of the waveform, which is what I was describing in a few slides ago, but the phase, how the phase changes over time. So let me explain this just in a slide. So I have now put here also the oscillating part of the strain, and the oscillating part depends on twice the orbital phase. The 2 is just there because of the quadruple formula. If you were using the dipole, you will have 1. So there is 2 because of the quadruple. And how do we get then the orbital phase? So we use on one side the binding energy of the system, which in an expansion in the velocity of the binary at leading order because of the barrier theorem, you can just write like the reduced mass divided by 2v squared. On the other hand, we have the luminosity, how much energy is emitted in time, and this comes, again, I wrote this expression before without the coefficient here. This comes from the paper of Einstein, although, of course, Einstein was not talking about binary systems of black holes and neutron stars in his paper, but it's just the quadruple formula. And then what you say is that, okay, the variation in the energy has to be equal to the minus the luminosity at infinity. And if you consider just a circular orbit, as I told you before, B you can write in terms of omega, and then you can rewrite this formula like omega dot minus the ratio between this, and then you can just integrate to get the phase. So there are two important things that you need to know: how the dynamics changes the binding energy and the luminosity at infinity. I mean, this is just for the inspiral part of the signal before arriving to the merger, and it's a very simplistic way of representing what we want to do, but it's actually really showing the key component, the key ingredients, okay? Binding energy and the luminosity. So I'm showing here just another video that represent the flux of radiation emitted by two bodies going around each other, two black holes, equal masses. This is the inspiral part until they merge with each other. And then you have the so-called ring down. Once a black hole forms, it just rings space-time, as we will see later. And you might have noticed here that the radiation, it's in all directions, but in particular perpendicular to the orbital plane. Okay? You see the two blobs up. And because there are no spin in these simulations, the orbital plane is fixed in space, is not actually precessing. You will see another example later. Okay, so we have to solve this problem, okay, to get the phase very accurately. And I want to just have a couple of examples to explain the complexity. So you have taken a course in classical mechanics, you know Newtonian gravity, that explain the motion of the planets around the sun. We have a beautiful formula that represents the orbit, okay, in this case. The situation is much more complicated in general relativity because we don't have an analytic formula, okay? The Einstein equations are nonlinear. It's not, there is no closed form solution of the two-body dynamics. And moreover, not only we don't have an analytic formula, but the ellipse, which in Newtonian gravity is fixed in space, it rotates in space, in general relativity. Remember the precession of Mercury, okay? And in our particular case, because the two objects are very close to each other, they are losing energy, the ellipse not just rotates, but also shrinks in time. So we cannot have a closed form solution, but we can rely on approximate models. We can do an approximate solution of the Einstein equations. We can also have a numerical solution by solving the Einstein equation on supercomputers. And in fact, over time, the two communities of analytic and numerical relativity have been working together to produce these waveform models that we need for the search and for the inference analysis. And just one word, to do the numerical relativity simulation I was showing you before, it takes between a few weeks and even 6 months of two black holes going around each other for 15, 20 orbits. It's very time-consuming to do these simulations. And so if we want to build a template bank for LIGO, Virgo, and Kagra, we cannot actually use numerical relativity. We have to build waveform models that put together numerical relativity and analytical relativity. So let me go a step forward. So in the parameter space that represent the binary mass ratio, separation, eccentricity, so numerical relativity is our best tool, but as I said, it cannot be used everywhere in the parameter space because it's very time consuming. So we have to use analytical solutions, and for that, sorry, I have to go out again because it's not showing. Okay. So we have post-Newtonian theory that covers a certain part of the parameter space. It expands the Einstein equations in powers of V over C or GM over RC squared, where R is the separation between the two bodies, weak field, and the slow velocities. Then we can build a post-Minkowskian expansion of the Einstein equation, which is an expansion in G or G over R, so weak field, but not slow velocities. So it resums all the velocity terms. And then if you have a small black hole going around a very large black hole, we can expand the Einstein equations in powers of the mass ratio. Then we can put together these approaches in the effective one-body theory, which also has a physical ansatz for the merger ring down, and is then improved by using numerical relativity simulations. and these waveforms are produced in time domain. Or we can use frequency domain waveforms in closed form. They are called phenomenological, by putting together the effective one-body approach, post-Newtonian theory, and numerical relativity. And in frequency domain, the waveforms are also quite simple. This is the amplitude in the different phases, including the merger here and the ring down, and this is the derivative of the phase of the waveform, not a very complicated function. Now, what is also important is that, especially going into the future, well, the black holes, the binaries, might be not just in vacuum. For example, in the case of a small black hole going around a very large black hole, the source is called extreme mass ratio in spirals, which are sources for the detector LISA in space. The small body could be in an accretion disk. The black holes could move in a certain medium, as you can see in this animation, and one could also consider theories that are beyond, beyond general relativity. And for that, if you are doing calculation using Feynman diagram, this means you have to introduce also new operators, for example, scalar fields to represent scalar tensor theory of gravity, or also to represent maybe the environment, the presence of a third body, or maybe dark matter, etc. Okay, so I have just one slide about the calibration. So, as I said, we have to use numerical relativity to improve the approximate models. And in this plot here, in the upper panel, you have a numerical relativity waveform in blue and effective one-body waveform in red. So you can see there are some differences between the two as the approach merge. So we tune the model to include information from numerical relativity until the model and the numerical waveform agree with each other. In producing the most recent family of waveform models in this SUBNR waveform model that we have developed in our group, we use 441 numerical relativity waveform, and you see them represented in the parameter space of the mass ratio and the binary effective spin. The different colors correspond to different mass ratio in the binaries. And then waveforms are used for the template bank, for binary neutron star black hole and binary black holes. This is the projection of the template bank in the mass plane. And at the low masses, LIGO and Virgo uses of the order of 75,000 post-Newtonian templates, just without even the mergering down, because the merger happens in the kilohertz, as I was telling you before. There are also other waveforms that are used for inference studies, the phenomenological ones, the TOB sum S, and the numerical relativity surrogates, which interpolate directly numerical relativity waveform where they are available. So they are limited in the region in which we have numerical relativity simulation in parameter space, but also in length, okay? Because they cannot be very long, it takes a long time. So once we have a detection, then this can be followed up with an inference study. And this is just an animation for the very first event that shows how the model is varied by changing the distance to the source, the masses in the binary, until the model and the data agree very well, okay, during the inference study, the Bayesian analysis. And from that, from the best fit, we can get the distance to the source, the masses, what was the final mass of the black hole that formed, what was the spin. And since we are physicists, we like the posterior distributions, and for the very first event, this was the posterior distribution for the masses, M1 and M2, marginalizing on all the other parameters. And you can see that the two waveform models used in the collaboration give results that are very close to each other, at least for this event. Okay, so what happened since then? Well, maybe some of you have already seen this plot. So this is the collection of all the events, 90 coalescences in the first 3 observing runs. So you have one black hole, another black hole, they merge and they form a new black hole, which is here. The black holes are in blue in this plot, and the neutron stars are actually in in orange. So this is the very first event. This is the binary neutron star, the first one. This is a still picture from the simulation. This is the most massive binary black hole that was observed. The black hole form after merger is around 150 solar masses. The most asymmetric binary black hole, I will come back to this in a moment, and the only event that has been published by the ongoing run of the collaboration detected the 29th of May 2023. And the collaboration is now going through an observing run, which is called O4, and has already announced basically twice the number of events that have been observed in the first 3 runs. And this is due to the improved sensitivity and also the longer period in which the events have been actually measured, observed. So let me give you some highlights. So the 14th of August 2019, a binary was observed with a puzzling companion because the primary mass is certainly a black hole having a mass of 23 times the mass of the Sun, but the secondary has a mass that is considered too high to be the mass of a neutron star and too small, maybe, to be the mass of a black hole formed from a collapse of a star. But the importance of this event is also the mass ratio, which you can see here, it's around 10. And the more substructure and complexity the binary has, for example, asymmetry in the masses, asymmetry in the spin, the richer is the radiation. The radiation does not contain only the dominant mode or harmonic, which is the number 2, but as you can see in this visualization here, the signal is decomposed. The signal here is decomposed in harmonics, which become more and more important as the binary approach merger, which you can see in this last part of the simulation. And on the left, there is the posterior distribution of the mass, the secondary mass, and only when in the models, Phenom and UBNR, one adds the presence of high harmonics and also precession, P, the posterior distribution are tighter, and one could get an error on the mass of the order of 10%, which in this case was important because of this puzzle that the mass is just 2.6 times the mass of the Sun. Few words about the event detected the 21st of May 2019. This is the larger binary black hole observed. Actually, there have been also another one with these masses, more or less, slightly smaller. This is a simulation that represents the event. The mass was so large that the event also lasted a very short amount of time. And this also is posing a challenge for theoretical astrophysicists because the mass of the 2 objects, and in particular the primary, is too large for people think a mass of a black hole should have formed from a collapse of a star because there is a gap, a theoretical gap that should be between 60 and 120 solar masses due to a phenomenon that is called pair instability supernova that basically leads the star to explode without leaving any remnant. But we are observing these masses. And these are the posterior distribution for the masses of the 2 objects for 3 of the waveform model used, in this case also the numerical relativity surrogate, because the event was short enough that one could use the best waveform at our disposal, which are numerical relativity surrogate. And here you see the determination of the spins in the binary, the effective spin, which is the projection of the spin along the direction perpendicular to the orbital plane, the angular momentum, and the spins along the orbital plane, which is the chi-p, which is the precession, tells you basically if there is precession. And you can see this is basically the prior in black. So there is some hint of precession. And also in these plots, you see more differences between the models, although still overlapping with each other, the posterior distribution at 90%, so we are not yet dominated by systematics. Okay, now let me switch to binary neutron stars. So I already anticipated that we have seen actually 2 events. The very first event that had also the electromagnetic counterparts, and then another binary neutron star. So the neutron stars are also quite peculiar objects because of their high density, in particular in the core, larger than nuclear density. But here the interest of gravitational waves is in trying to understand, unveil the internal structure, the composition of the neutron stars. especially in the inner core, okay? And so how can we do that? Well, we can do that because the neutron star have a parameter which is 0 for black holes. It's called the tidal deformability parameter. It measures, is basically the ratio between the quadrupole moment of the neutron star divided by the external tidal field of the companion, and the coefficient lambda depends on the equation of state of the neutron star. So how can we actually measure it? Well, if you take a binary neutron star, a binary black hole with the same masses, they agree very well at large separation, the waveforms, but as they approach each other, because one has the tidal deformability and the other not, you can see the difference that becomes larger and larger going toward merger. Of course, also the merger of two neutron stars is very different from the merger of two black holes, as you can see here, but actually you can extract information even before arriving to the merger. There have been a lot of studies. I just took this paper from this plot from the LIGO-Vigo-Kaga collaboration that shows you the result after the observation of 170817 for the pressure and the density constraint at 90-95% confident regions, and this is rho nuclear, twice the nuclear density, etc. Also, one could put a bound, actually measure the radius of the neutron star, and you can see around 12 kilometers with an error of 10-15%. Of course, the very first event of neutron star merging with each other is very well known for all the electromagnetic counterparts that were observed. So this is the track in frequency time domain of the event observed by LIGO and Virgo. And you can see from Fermi and integral, after 2 seconds, a gamma ray burst was observed. And this is the reconstruction of the event in the sky. In particular, thanks to Virgo, the localization was around 70 square degrees. And after 11 hours, 9 hours, 11 hours, the telescopes on the Earth, there were 5 of them, particular SWOPE, could identify a little dot here, which is very close to this galaxy here in black, which was not present when they took the picture of the galaxy around 21 days before. And that event was associated to the remnant of the binary neutron star. So anyway, this event was followed by many, many other telescopes looking that could observe X-ray, infrared, radio. I mean, this was actually the kilonova event that you see here. There was an independent measurement of the expansion rate of the universe. The Hubble-Lemaitre parameter was observed with an error 15-20%. And finally, by combining the gravitational wave and the gamma ray burst observation, one could actually bound the speed of the gravitational waves very, very well, less than 7×10⁻⁻16, which is really, quite remarkable. Okay, forgot. So another important thing is that when the two neutron stars merge with each other, they actually expel materials which is very rich in neutrons, and people have concluded from the observation of binary neutron star that actually the majority of the elements, heavy elements in the periodic table, including gold and thorium, uranium, and plutonium, are actually produced in the merger of neutron stars. Before, there was not clear whether these heavy elements would be produced by the coalescence of neutron star or from supernova or dying low-mass stars, as you can see here in yellow. Okay, not surprisingly, after binary black hole, binary neutron star, also a mixed binary, a neutron star, a black hole, was observed during the third run, the 15th of January 2020. And this is a visualization of a simulation done by Charosia and Dietrich. You can see now the neutron star being swallowed by the black hole completely, leaving actually not much disk around in this example. The presence of the disk depends on the mass ratio in the binary, the spin of the black hole. And from this plot here, you can see actually, if you focus on the blue curve here, the reconstruction of the masses, the primary mass and the secondary mass for this event. Since no tidal deformability could be measured in this event, the only way we could conclude that there was a neutron star was actually the mass of the secondary that you can see in this plot here, which goes between somewhat 1 and 2 solar masses. Also, this event had not a very good localization in the sky, so one could not get any electromagnetic counterpart if there would have been electromagnetic counterparts, because, as I said, that depends on the properties of the binary. Now, a few words about the only event that until now has been published by the LIGO and Virgo and Kaga collaboration was observed the 29th of May 2023. It's a beautiful neutron star black hole, we think. So the secondary mass is clearly neutron star. The primary mass, well, we think even within the error that this maybe is not a neutron star, it's a black hole, is the smaller black hole that has been observed until now. And in fact, even taking into account the errors in the mass, it squarely fits in this low mass gap, which is a region between 3 and 5 solar masses where we have not seen, we are not seeing black holes in X-ray in our galaxy. So this plot again shows the posterior distribution, two-dimensional one for the masses and 1 and 2 of the event. So the event is this one in green, contrasted with the other neutron star black hole that was measured, which is the one in blue here. And this is 1708, no, sorry, this is 170817, and this one was the most asymmetric system that I was discussing before. Okay, no tidal effects also were measured here, and interestingly, the primary object spin is anti-aligned with the orbital angular momentum. Okay, I want to say a few words about the tests of general relativity that have been, the tests of general relativity that have been done until now. Okay, a bit more. So I want just to mention 2. So the first one, so first I want to say that these tests are very different from the one that happened in the solar system, also in cosmology, because one is probing the high velocity, highly dynamical regime of gravity. And I want to mention, first of all, spectroscopy. So black holes are like bells. If you perturb them, they ring the space-time. They have quasi-normal modes, frequency with a frequency complex one, frequency and decay time. And this is what happens at the very end of the merger of 2 black holes. You see that is when they merge, you form a new black hole, and the black hole rings, as we say, the space-time. Now, in the same way, electromagnetic spectral lines can identify chemical elements, hydrogen, neon, beryllium, etc. Actually, it turns out that the quasi-normal modes in general relativity, they only depend on the mass and the spin of the black hole. And so if you can measure the quasi-normal modes, you can actually extract the mass and the spin, and you can, if you measure more than one, you can do consistency test, and you can prove whether the black hole that formed after merger is a black hole in general relativity or not. And the only thing I want to say here is that general relativity has passed all the ring down tests so far with flying colors, so no problems. The other test I wanted to mention, it's a test that resembles, maybe some of you know about the parametrized post-Newtonian test that is done in our solar system to test the theory of general relativity. So here, what is done is that if you take the frequency domain waveform, it has an amplitude and a phase, and the phase can be written as a polynomial in a velocity in the post-Newtonian expansion. Now, the red coefficients here are prediction from general relativity, so they describe physical effects like spin orbits, spin-spin coupling, tidal effects, absorption, tails, etc. So now you can introduce a parameter which is 0 in general relativity, but you leave this parameter free. And when you do the inferior and the Bayesian analysis, besides the 15 parameters that describe the binary the waveform, you also vary these parameters one at a time. And you get a posterior distribution when you marginalize all the other parameters for each of them. If they encompass 0, general relativity is not violated. And until now, we have not seen any violation. So one could put a bound on these parameters. And this is the result. So for each of these columns, you have a post-Newtonian order. This is minus 1 pm, which is what I wanted you to catch your attention. So minus 1 pn means dipole emission. If you are in a scalar tensor theory of gravity, the leading emission is not the quadrupole, but the dipole. And by considering different events, and in particular the binary neutron star, one could put the best bound with gravitational waves on the dipole. This bound comes from the binary, the neutron star black hole binary I was just describing. Because of the masses quite small, the signal was very long. And so it could put actually a quite nice bound. And in this case, the bound is very important because there is a black hole in the system. And I will not have time to describe the other data here, but these are just the bounds when you put together all the events for the different post-Newtonian parameters. And the bound can vary between 10% or less than 10%, as you can see here. Okay, so now I want to describe a moment in the future. I have 4 minutes. Is okay? Okay. Okay, so let me tell you now about the future, which is also very exciting. So we are, so LIGO and Virgo are at the 4th observing run, okay? The numbers here corresponds to, in megaparsec, the distance at which one can observe a binary neutron star and claim a detection. And the fact that the number is increasing means basically that the interferometers are becoming more and more sensitive. In the current run, the LIGO detectors achieve 160, the Virgo is around 60 megaparsec. So the O4 run started in May of last year and is going to last until June of next year. And has already reported this number of candidate signals, as I said at the beginning. So after, and you see Kagra, that will actually join the run sometime in the spring of next year if they will achieve a distance, a sensitivity up to a distance of 10 megaparsec. So there will be a break of taking data, and then there will be the last run in this decade called O5, hopefully at this much larger sensitivity. One hopes to have LIGO India in late 2020 or more likely beginning of 2030s, and there will be some upgrades of LIGO and Virgo for the next decade, at the beginning of the next decade. But they are still looking these interferometers around, less than 1 or 2 in redshift. So we expect new facilities on the ground, Einstein Telescope in Europe and Cosmic Explorer in the US. And here you see the improved sensitivity of these detectors with respect to advanced LIGO, improving at low frequency, and so bringing in band, in particular, masses, black holes, more massive than the one that we are seeing today. I was telling you that what is important is the merger frequency. If the mass of the black hole is too large, the binary merges outside the bandwidth, which starts around 20 hertz for the current detector. So if you improve a lower frequency, you can see more massive systems. And because they are more sensitive, you can see even up to, very large redshift. The number of events is going to be very large for binary black holes of the order of 10,000 events with a signal-to-noise ratio 10 times better than what we generally see today. And the signals can be also much more complicated because now if you have a large black hole, 1,000 solar masses, and a small black hole of around 10 or a neutron star, it does many, many, many cycles. So the dynamics is much more complicated. So I skip actually this slide, which is saying the same information because I want to go to the end. So we will have LISA. This is sure. LISA has been adopted as mission by ESA at the beginning of this year. The launch is expected for 2035, in 10 years. And the LISA will open a new frequency band around the millihertz. You can see here the track of massive binary systems of a million or 10 million solar masses sweeping in band. One can see also extreme mass ratio in spirals, and white dwarf binaries in our galaxy, which are all these actually gray regions here. Extreme mass ratio in spirals are small black hole going around a large black hole, probing the space-time for millions of cycles with exquisite precision. And these signals, differently from the transient signals that we are seeing today with LIGO, Virgo, and Kagra, we are going to see signals all the time. And so that analysis is going to be much more complicated for these signals. So for that, we need to improve the waveform models to include not just quasi-circular orbit, but generic orbits, take into account the environment where the black holes and the neutron star are, possible perturbation from third bodies that can perturb the motion of the binary. We have to take into account also effect due to gravitational lensing. In this plot, you see the lens signal in black, and the lens signal, depending on the mass of the lens, in color. Depending on the mass, again, it could create also multiple signals, as you can see here. So we have to improve the solution of the two-body problem in general relativity, and in the last few years, there have been a lot of work, new tools brought in the classical general relativity community coming from scattering amplitude, effective field theory, quantum field theory, and you have people also here working actually on this topic. So there is a lot of work to do, and in fact, the frontier in waveform modeling is actually the eccentricity. So you saw this animation before, but now the waveform is much more complicated. These are the polarization, and this is due to the fact that the motion is happening along an eccentric orbit, and all the spikes that you see here are the points of periastron passage of the two objects. And so we would like also to have template banks with eccentricity, with spin precession, etc. Now I have my last slide, and then the end. So I wanted also to highlight two aspects that are important for the future, not just accurate waveform models. We will have many events. I mentioned before 10,000 binary black hole in 1 year with large signal-to-noise ratio for Einstein telescope and cosmic explorer, but also LISA will have many events. And several groups have started to develop machine learning methods to address the problem of a large number and longer gravitational wave signals. And I wanted to give you just a plot from a recent paper using a code that we have developed with our collaborators at the Max Planck for Intelligent System called DINGO, and also now University of Nottingham in the UK, that show you the results of an inference study that can be done for a binary neutron star, very long signals, even for Einstein telescope and cosmic explorer, in just 1 second, using machine learning. Normally, these studies could take several days, if not a week. And this will be very important for alerts for astronomers. And finally, the big challenge is this famous global fit of LISA. Okay? So many signals will be present at the same time. And the idea, represented by this cartwheel, is that, okay, you have some data, you start subtracting the first signals, then you detect them, you subtract, and look for what is actually in the residual. Maybe the residual will be a supermassive black hole. And then you subtract and you proceed. And then over time, the signal-to-noise ratio increases, so you repeat this in such a way that the problem converges to something. Now, in this process of subtracting, you have to be very careful that you subtract everything from the signal and you don't leave residuals, because otherwise you are going to be affecting the next signal that you want to extract. So this is a very important problem that many people are working on now. So my last slide, so I just want to say that with the first two observing run, the tip of the iceberg of the binary population was discovered, in the sense these signals were more or less vanilla, equal mass black hole, non-spinning. The third run has already revealed a much richer picture, and several so-called exceptional sources were observed. O4 is ongoing, many signals, And the first paper, I think, will come out sometime in the summer. So we have to wait to see what the data are saying. There are several outstanding questions, including the presence of the signal where we see either objects in the low mass gap. We don't know what they are. Maybe they are black holes, neutron stars. Also, there is the open question, what are the black holes in the high mass gap? Because theoretical astrophysicists will say we should not see these black holes. Well, bright future, as I already said, many signals to be observed with diverse properties, much higher signal-to-noise ratios, and a lot of work to be done from the point of view of waveform modeling, but also, as I was mentioning in my last slide, also in data analysis. I want to thank my department. A lot of work that I was highlighting actually was done by many of them, and of course also the LIGO and Virgo and Cagra collaboration, and also LISA and the Einstein telescope. Thank you for your attention. Sorry to take a few more time.
Thank you very much. So we have time for questions.
Thank you. Exciting field. There's one thing I got confused by, which is you mentioned that for neutron stars, you're sensitive to the tidal deformability and equation of state. Now, naively, I would have thought you're primarily sensitive to viscosity. What's wrong with my naive expectation?
So viscosity, you mean, what do you mean by
so like in the Earth-Sun system, if you measure what the P dot of the moon is, that depends primarily on not the tidal deformability, well, that too, but the biggest effect is the dissipation rate of ocean waves. So the dissipation that, at least for the Earth's moon, dominates the recession. But you're saying it's not dissipation, you're saying it's the actual instantaneous particle moment.
Yeah, but I mean, at the end, you see the kind of result that we can extract are mainly in that plot I was showing about the pressure and the density. Then you can have models, you know, in nuclear physics that can explain, you know, how you relate, you know, whether your model for the pressure and density inside the neutron star is within the 90 or 95%. But I actually think that there is not a lot that we can say in, I mean, we call it the equation of state, but at the end it's just P versus rho is the equation of state. So I think, are you questioning that plot in the sense we can extract P versus rho, right? We can constrain that.
Well, but P and rho are ideal fluid parameters. Because I would have thought in the Earth's moon at least, you're dominated by non-ideal, so viscosity specifically. So how gooey this thing is, and not so much how much it deforms. But maybe I'm missing.
Okay.
I think I'm just missing the leading order effect. So I guess I need to read up on it.
Sorry. You mentioned you can probe at the center of the neutron star using gravitational wave. Could you elaborate that a little bit? And my second question is, in the Einstein equation, the cosmological constant is missing. If I add that back, will that perturb any of your mass determination, VLC determination, depending on how far the binaries are?
Okay, maybe I start from the last question. So the cosmological constant, you mean that we should take into account the fact that the expansion of the universe. So at the level of the motion of the binary system, of course, the expansion of the universe is not affecting because, only the gravitational... for what I remember, people are trying to understand if there is, an effect, but it's incredibly small. So it's not really, has no effect at the end. The cosmological constant has not has not an impact. But of course, people, for example, have looked at what if the propagation of the gravitational waves is not the one that we expect. If the graviton have a mass, for example, then the dispersion relation will be different. And this is something that LIGO and Virgo have put a bound on the mass of the graviton or the Compton wavelength associated to the gravitational waves. So about your question on the, the equation of, the internal part of the neutron star. So for what I understand, of course, neutron stars, as the name says, are made of many neutrons. But when you go in the internal part, in the core, you have just quarks, right? And so people have been looking at the present. For example, there could be also phase transitions. And they could also have an impact on that, parameter that we measure. Or, for example, depending on, again, the equation of state, so it depends on the presence of hyperons or pions, of kaons, etc. This can have an impact on this parameter that one wants to measure. But I think there is also a lot of degeneracy, I have to say, for what I understand. I mean, there is a lot of degeneracy between all this information with respect to really the parameter that we can extract. Okay?
Well, in the kilonova case, you mentioned that there was a kilonova case.
Kilonova.
You mentioned there was a time delay between the gamma ray burst
Yeah.
and the gravitational wave event. What is the current explanation for this time delay?
You mean the time delay of 11 hours or the gamma ray burst time delay of 2 seconds?
Yeah. Like
Which one?
The gamma ray burst from the gravitational wave event.
Yeah. So let me go back a moment to that. Sorry, I think I went too far.
Yeah, over there.
So there are 2 things. One is the 2 seconds of difference.
Yeah.
Are you referring to this?
Yes.
Yeah. This, for what I understand, people think it takes some time for the jet, so the 2 neutron stars merge with each other. In the most plausible explanation, a black hole is formed, and a black hole triggers a jet. And it takes a little bit of time for the jet to penetrate the material which is around, at that point, the neutron star, because there have been material ejected. And for what I understand, these 2 seconds is basically the time for the jet to go out and then being seen, observed. This is what I understood. Yeah.
I'm curious about your ability to detect or constrain non-standard models, so non-GR, non-black hole type models in the matched filtering process. How extensive is the library of filters that you're applying that come from non-standard models, and do you want a more exhaustive library of those? And are they sharply different in some cases from the standard picture?
Yeah, so at the moment, the only template bank that is used by the LIGO and Virgo collaboration is made of general relativity templates. And also, it's even just 4-dimensional, the 2 masses, and the spin's projection along the direction perpendicular to the orbital plane. So what is done after the detection, then one uses so-called parametrized models, which is the one I gave the example. You add these parameters. Of course, because it's parameterized, this means you are expecting small deviations from general relativity. So until you are, if you consider small deviation from general relativity, these parameterized tests, which are done also for just the ring down, for example, can be quite, I would say, robust. Okay. Then this is not done as part of the collaboration. People outside the collaboration that use the data, the public data, they've started, because now we have some example of more templates in a specific theory of gravity, which is not general relativity. For example, Dilaton-Gauss-Bonnet, just to give an example. So the first inspired merger in down waveform have been produced. But again, one is following up events that were first discovered with a GR template bank. Now, yeah, it is interesting, of course, the point, can we look at, yes, we can, but do we expect big deviations? Of course, we don't know. One test which I think is important, which is still done as part of the test of general relativity paper of the LVK, you look at residuals. So suppose that you detect a signal, and with a GR template, you then look at the best fit templates, not from the search, but from the Bayesian analysis. If you subtract from the data, the signal, the best fit, if you look at the residual, you should see that they are distributed in a Gaussian way. If they are not, if you see a strong correlation, that should be a hint that the signal maybe was something else. But until now, we have not seen any, anything that would create an alarm of that kind. That would be an agnostic, so without it, if you want, it's a way of testing the use of the templates. Finally, I want to say there is another search which is done, which is called the burst search. From the name, it's looking for signals that are very short, but it's unmodeled. You use basically wavelets, sine Gaussians, etc. So it doesn't use templates from general relativity, but you can do that with signals that are very short, because if the signal is very long, that's not very effective. But of course, if people have other ideas of how to do the searches of unknown signals, it would be nice.
Well, actually, maybe I can follow up on this question.
Yeah.
Since the question was coming from a member of the Event Horizon Telescope. So
I didn't know that.
yeah. No, so I'm actually just wondering, is there complementarity in these tests? Could you imagine things being tested, by both the Event Horizon Telescope in terms of modifications of gravity near the horizon versus ring down effects?
Yeah, I think that there is complementarity, because in any case, the test that the Event Horizon Telescope is doing is still a fixed background. So you have K, which is not dynamically changing, right? I mean, it's a given, and then you can study the motion of photons in that background in a strong field. So here, even in the ring down, there is the beginning of the ring down, which is a dynamical phase because the two black holes are merging with each other. The last part, okay, it's, the Kerr space-time are settled, and so there is more complementarity, and there are some points of contact, I think, between the two.
Thank you, Alessandra. I can ask a question, right? So,
Yeah,
so since you mentioned machine learning at the end, so I wonder what's the perspective for using machine learning for like waveform generations? Like, is there any room there, or is there big obstacles there?
This is a very interesting question. Of course, we are thinking about that. Until now, has not been used to generate. So it has been used I think in a couple of papers to try to interpolate the waveform that are known in some part of the parameter space, but not at a level that we can really use it, in the large portion of the parameter space that is used for research. But it will be very interesting if we can use machine learning AI to predict, given the information from some part of the parameter space coming from numerical relativity, or the models that can provide information, especially at low frequency, during the spiral, to maybe be able to predict the waveform where we don't have yet a solution from a full numerical relativity simulation. I'm very interested in this, but until now, we have not actually made a lot of progress on this. Normally, so until now, the machine learning has been used mainly to train. You train the network with waveform that you know, and then it can accelerate the inference. That has been very good in that. Yeah.
So, naive question. So you mentioned that in the future, one can expect to measure, for example, the signal coming from very far, like up to redshift of 100. And maybe you expect like hundreds of thousands of signals coming from different places. So in that case, the current approach of filter matching how can it be applied to, like, in the case where you have a lot of signals and then the signal may actually overlap with each other?
So you mean the current approach of match filtering, right? Yes, indeed, this is already a problem for all the analysis that has been developed, that is under development for LISA. So the global fit, so in the global fit, for example, you still will have to detect the extreme mass ratio in spirals. The global fit does not allow to detect, it's not the way in which you will detect them. And in fact, people are looking at, for example, ways of, these are very, very long signals that will last for millions of cycles. Maybe a coherent analysis cannot be done, and people are exploring ways of dividing the signal in several pieces, and then analyzing, each of them, and then trying to see the coherence between them, semi-coherent way. And the fact that they overlap with each other, that is the global fit. So once you have detected, then you subtract and you look for the residual, and then you continue. So you have to put together now different ways of doing it. But I want also to mention that for pulsar signals, which we have not detected until now, they are also continuous waves. They are there because the pulsar is rotating, and so they accumulate the signal for a year, and they also use semi-coherent ways of doing it. It's very complicated, very complex analysis, but this is what we have to do with many signals in the future.
Hi. So can you explain that how the gravitational waves is used on calibrating the expansion universe? Like because the distance from a signal to us is a quantity that inferred from the waveform, right?
Yeah.
So how do we can use this to calibrate the expansion?
Okay. So indeed, the waveform are standard candles or standard sirens because. So the idea is that imagine I wrote, you have h equal to 1 over d, the distance, and then there is all the rest. Well, when you do the Bayesian analysis, you are basically measuring all the parameters. So in that sense, you don't need to calibrate, you are just measuring the parameters. Of course, the parameters come with an error. So at the end, you are measuring the distance with a certain error. But that's, it's intrinsic, the measurement of the distance. You don't need to calibrate. You see what I mean?
Yeah, okay.
There is some degeneracy because the signal is also proportional to the inclination angle, which is the angle between the direction perpendicular, let's say, to the orbital plane, if you don't have spins, and the direction of the gravitational wave emission. And so if you can measure the inclination in some other way, you can measure better the distance. Otherwise, the distance has a large error.
Thank you.
Yeah.
If one of the black hole is charged, then a black hole merger, for example, could emit electromagnetic emission. Is there such an observation?
Okay, we think that the black hole, the astrophysical black hole, do not have charge in the standard model, but the test I was telling you about the dipole emission, that is actually also a test of the possible presence. So this test here, the dipole emission is basically proportional to the difference square of the charges of the two objects. So if the black hole was charged, then we would be seeing the difference in the charge square of the two of them. So you cannot measure directly the charge, but the difference between the charges of the two black holes. That's a way of bounding. In fact, some people have used it to bound the charge that the black holes could have.
Thank you.
You're welcome.
Any more questions? Last final chance.
No question, okay.
No, so if not, then let's thank Professor Buonanno again.
Thank you.